This is part 3 of our lecture 1, and in this part we are going to discuss how we can draw the equivalent circuit for the op-amp using the features that we discussed in our previous segment, the part 2, and we'll also see how we can connect the op-amp in a circuit, what are the different ways of connections, and we'll see what are the different applications for the op-amp that we can have. Okay, so now that we have learned the different features of the op-amp, now we'll see the using those features, if you can develop some equivalent circuit that can be useful in understanding the impact of these different features in circuit applications. So here we show the op-amp circuit symbol again with the different features. RID, if it is infinite for the practical ideal op-amp, it will be current will be 0. So practical op-amp, finite RID, this current should not be 0. It has a finite open loop gain and should have non-zero output resistance. So then this is the circuit that we can use to represent the op-amp, right? Equivalent circuit. This is not what we have inside the op-amp. Inside the op-amp we have many transistors connected in a special fashion, but that is how we can represent the circuit. Represents the behavior, how it will behave at the input and at the output side. At the input side you will be applying voltages, and what the voltage will see a resistance posed by the input side of the op-amp, and that resistance will define how much current can flow, right? And the output side, what do we get? We get an output voltage, and that voltage will be a function of the input voltage VID. So the output voltage is the input voltage multiplied by the gain of the op-amp AOL. So output side of the op-amp behaves like a voltage source. That is voltage dependent voltage source. So it is represented by dependent voltage source, and the voltage depends on this input voltage VID. So we have this dependent voltage source, and if you look from the output side, definitely you will see some resistance, and that resistance comes in series with the voltage source. So that is how output side will look like. We can represent output side with a dependent voltage source in series with the output resistance, and that's what is known as the equivalent circuit of the op-amp. Any amplifier will have similar equivalent circuit. The difference here, for other amplifier, regular amplifier, will have single input, so we'll have just input here, this side will go to ground, right? And the output side will all remain same. Instead of AOL you will have just gain A, and here instead of VID you will just have VI. So that will be the difference, but in general the equivalent circuit will be similar. Okay, so that is for practical op-amp in how it will look like, the equivalent circuit. So now that we have learned the equivalent circuit for a practical op-amp, now we'll see how we can draw the equivalent circuit for an ideal op-amp from that of the practical op-amp. So the features that we have for an ideal op-amp, the RID is infinite. We have infinite input resistance. For practical it was finite. So the infinite input resistance means that current should be 0. The open loop gain is infinite, and also the output resistance is 0, right? So what does that mean in terms of our equivalent circuit? So this was our equivalent circuit for the practical one. So now RID is infinite, so it becomes open circuit at the input side, and as you can see that the circuit becomes open, so current should be 0 here, but shown here in the circuit symbol. And the output resistors are not is 0. For practical, we had a non-zero output resistance, but for ideal op-amp, R0 should be 0. That means we'll have a short circuit here. So at the output side, we just have a voltage dependent voltage source, which depends on the input voltage VID, and it directly connects to the output. So that is how it will look like for the ideal op-amp. Now, the circuit connection. How we can connect op-amp in circuit? We can connect op-amp in two different ways. One is called the open loop connection. The other is called the closed loop connection. So the diagram here that shows, right, just the op-amp. So this is actually our open loop connection. We have two inputs, V1 and V2. You just apply or connect the two inputs at these two terminals. You directly apply whatever input you have to these two terminals. This gets connected to the supplies. You take the output from here. So as it is, circuit as it is. This shows the op-amp in open loop connection. And next, so there is in some detail. That means this also shows the supply voltage. If you don't show the supply voltages, then this is how we can show without the supply voltages. So this little bit simplified open loop connection circuit diagram. Now closed loop connection. So how does it look like? In closed loop connection, you will have to connect two external resistances, which are shown here as an R1 and R2, and that is how you connect. The R2 connects the output to the inverting input terminal, and another resistor is R1 is connected to the inverting input terminal. And circuit like this, right, when you have these two additional resistors connected to the op-amp, is known as the closed loop connection. Here R2, it closes the loop around the op-amp, right? From input you go to output, from output R2 back to the input again. So that is the closed loop, right? That is completed by the resistor R2, and so this is known as the closed loop connection. In closed loop connection, again we can have two different configurations. Since you see that we have two terminals here dangling, so we can apply input to either this terminal, or we can apply input to this terminal. If you apply input to this terminal here, then you ground this one, and that is known as the inverting input terminal, because this side is the inverting input of the op-amp, and you are applying the input here to the R1, and that is being applied to the inverting input terminal through R1, so it's called the inverting amplifier configuration. The other configuration you can apply to the other terminal, and you ground this R1, so you are applying here directly to the non-inverting terminal, and so this configuration is known as the non-inverting amplifier. So in closed loop you can have two different amplifier configurations, inverting and non-inverting. Okay, so let's have a quick look about the applications that we can have with the op-amp. We have discussed about the two different connections, the open loop and closed loop connection, and they have different applications. In open loop connection, you can use the op-amp as a switch, as a comparator circuit. Comparator circuit means a circuit that can compare between the two inputs that are applied to its input terminals. Also, in closed open loop connection, you can use the op-amp as a detector, as a voltage level detector. Closed loop connection, we can all have many different applications. Like, first of all, we can use this as an amplifier. In open loop, interestingly, we cannot use the op-amp as an amplifier. But in closed loop, we can use the op-amp as an amplifier, and not only as an amplifier, we can use this also in many different applications. Like, we can use this to add signals, so called adder circuit. We can use the op-amp to amplify differential signals, difference between the two input signals. We can use the amplifier to integrate or differentiate You can use this as a voltage buffer circuit that is used to transfer the voltage from one circuit to another circuit without any loss. We can use the op-amp to design filter circuits. We can use the op-amp to design oscillator circuits. So you can have many different applications, right, with the closed. Okay, so now that we have finished our discussion on the introduction of the op-amp, now let's test ourselves how much we have learned, or how much do you remember what we have discussed. So first, draw and label the pin diagram of an op-amp. So that's important, because if you go for practical application, you need to know which pin is what, right? And we introduced some new terminologies here for the op-amp: the differential input voltage, differential input resistance, the open loop gain, the bandwidth. These are very important parameters that we'll always need when we analyze or design the op-amp circuits. And the features of the ideal and the practical op-amps, how they differ. The op-amp, as we have said, is a specially designed amplifier that has properties which are much superior than those of general purpose amplifier. So it is important to understand the features of an ideal amplifier, an ideal op-amp, and how the features of the practical op-amp deviates from those of an ideal op-amp. And then we need to also know to draw and label the equivalent circuits for the ideal and practical op-amp. That is very important when you go for design and analyze the op-amp based circuits. And last of all, that we discuss the circuit diagrams, how we construct the different circuit diagrams both in open loop and in closed loop connection using the op-amp, and what are the applications. So that's it for today, and hope you enjoyed the lecture, and see you in the next lecture. Goodbye.